Hi, this is the part two of the set partitions lecture. So we are going to continue off from part one, where we are talking about how to split a set into several blocks, right? We took a few examples in that video, and we got the values of, say, S of 5, 3, and so on. We got S of 5, 3 was 25, and S of 4, 2, and all. A couple of examples we saw in the previous video. So now what we want to do is we want to generalize that concept. And the generalization of that involves a class of numbers called Stirling numbers. And this is what this video is about. So let's do the definition. So the definition of this is, let n and k be positive integers. Then the number of partitions of n into k blocks is denoted by this symbol S N K, and this is called a Stirling number of the second kind. So let's think about what are the values of the Stirling numbers. So we'll start off with S of Nk is equal to 0 if k is greater than n. So why is that true? Obviously, if you have a set of, say, 1 to n, and you have to divide it into how many partitions? K partitions. If k is bigger than n, then this doesn't satisfy our condition where we have to split it into subsets where subsets are non-empty, right? Suppose you have to split it into n plus 1 subsets. Then it is obvious that one of these subsets will be 0. So that means that that is not a valid partition. So if any b1, b2 becomes phi on a null set, then that is not a valid partition. So you cannot partition Snk if k is greater than n. Therefore, the value of Snk is assigned to be 0. The second thing that we will see here is Sn0. What is this? So obviously you have n numbers and you have to partition them into 0 partitions. So that's obviously is 0 if n is greater than 0. By definition, we are defining S00 to be 1. Basically, there are 0 numbers and you have to partition them into 0 things, 0 blocks. So that is obviously going to be one way to do that. You don't have to do anything. So that is by definition, S00 is 1. So in the previous video, we saw basically S53 was 25 and S43 was coming out to be 6, right? We saw that 5 children were partitioned into 3 different rooms, identical rooms, and we did that problem and it came out to be 25. And similarly, 4, 3 was coming out to be 6. So now we will generalize these principles. There is one more thing that I want to talk about here. S of n1, right? What is this? So this is going to be equal to S of n, that is equal to 1. Why? The first Stirling number, let's look at. This is n things and you have to partition into one block. So that obviously there is only one way to partition that. There is only one B1 that will form. That will be the entire set 1 to n, right? And here you have n. So n things have to be partitioned into n parts, and each part has to be disjoint non-empty. So each part will contain one element. So there is only one way to partition that, right? Notice here that it is not an arrangement. The arrangement of sets B1, B2, Bn doesn't matter because B is a set of subsets, right? We discussed this in the last class. So it doesn't matter which one is called 1 and which one is called 2 and so on, right? So this is also going to be n. So now that we have a few of these values of Stirling numbers, we want to generalize it and say how to find Stirling numbers in case we need higher values. So that is a generalization that we were talking about in the previous video. So let's try to do this. There is a theorem that we want to prove. This theorem is saying that for all positive integers n and k such that n is greater than equal to k, we have S of nk will be equal to S of n minus 1 k minus 1 plus k times S of n minus 1 comma k. So this is called a recurrence, and this recurrence will help us calculate the values of higher and higher Stirling numbers. So let's try to understand why this is supposed to be true, right? So we'll do a combinatorial argument to prove this recurrence. So we'll show that both sides are counting the same thing. So think about what this left side counts. The left side means it counts partitions of this set 1, 2 till n into k subsets, What about the right hand side, right? So right hand side, we will split that into two ways, two cases basically. So the case one is when the element n in this set forms a block or a subset by itself. And case 2 obviously will be when element n does not form a subset by itself and therefore is part of some other subset. And we are, in both the cases, we are trying to do what? We are trying to count the total number of partitions of n into k subsets, right? Total number of partitions of this set into k subsets. Now in case 1, it is easy to count. If the element n forms a subset by itself, there is no other element in that subset, then we have already gotten a subset n, right? So if I want to construct my partition, I have to create how many more subsets here? I have to create k minus 1 subsets. And how many elements are available to me? N minus 1 elements, right? So if I count the number of subsets that we can create here, that along with this n subset will make the total partition, right? So this number will basically simply be s of n minus 1 comma k minus 1, right? Basically, we are taking n minus 1 elements, creating k minus 1 subsets, and obviously we have already had a element n as one subset, which is by itself, right? So this number is saying, this number basically counts all possible subsets, all possible partitions where n forms a subset by itself. Now let's move on to case 2. Case 2 means that n is not forming a subset by itself, right? So n is part of some other subset. So the first thing that we will do is take the other elements, right? Take the other elements, n minus 1 other elements, and we'll form k subsets. We'll form k subsets out of them, right? Because we have to finally make k subsets. So that number will be s n minus 1 comma k. So this is the set of n minus 1 elements have been divided into k subsets. Now we have to put element n into one of these k subsets, right? Because n is a part of some other subset. We have already created k subsets here. So how many choices are available for the element n? There are k choices for it, right? By multiplication rule, we can say that we can place the element n in any of the k subsets here. So this possibility is counting situations like this, where you have 1n and 2 and 3 and so on, where n is part of this subset right now, or n could be part of any of these subsets, right? So eventually now we are getting case 1 is this, case 2 is this, and the addition basically counts all the ways in which you can partition 1 to n into k subsets. Why? Because these two are mutually exhaustive, right? These two cases cover everything. Either n will form a subset on its own, or n will be part of some other subsets. There is no case 3 here, right? So therefore, we have proved that eventually you are counting the partitions of the same set 1 to n into k subsets. So this is a combinatorial argument for the proof. If you have any doubts, think about it, pause the video and think about, go over the explanation once more. It should be fairly clear. What we'll do now is evaluate take some examples and see how we'll apply this principle. So I'll just write the recurrence here. S of nk is equal to S of n minus 1 k minus 1 plus k times S of n minus 1 comma k. So now suppose as an example, we want to find S of 4 comma 2, right? S of 4 comma 2 means partition 4 element set 1 2 3 4, let's say 1 2 3 4 into two blocks, right? So let's see what we can do here. So to find S of 4 2, we'll apply this recurrence. So it will be S of 4 minus 1 3 2 minus 1 1 plus k. K is 2 here, so 2 times S of 4 minus 1 3 and k is 2, right? So we have converted S of 4 2 into S of 3 1 plus 2 S of 3 2. Now we know the value of S of 3 1 because 3 element subset into one partition is only going to be in one way, right? So this is going to be 1 plus 2 S of 3 2, right? S of 4 2 has become 1 plus 2 S of 3 2. And now we just need to find S of 3 2. So S of 3 2 will apply this recurrence again, is going to be S of 3 minus 1 2 2 minus 1 1 plus 2 into S of 3 minus 1 2 and 2 is there, right? So now we know that S of 2 2 is also equal to 1 because two elements into two blocks, that is only one way, right? And so this becomes 2 1 plus 2 into 1 and 2 1, two elements into one partition is also one way, 1 plus 2 into 1. So this is 3. We have gotten S of 3 2 is 3, and putting back the value in this, right? We get the value of S of 4 2 is 1 plus 2 into 3, which is 1 plus 6, so 7 ways, right? So we have taken this example in a way to illustrate the recurrence, how to calculate it, but we can also do it directly. Like suppose you have 4 element set, you want to divide into two blocks, right? You can have two types of blocks basically. You can have a block where one block is of size 1 3 and the other type is 2 2, right? So the number of ways to do this will be select 3 elements to form this. So it is 4C3, 4C3 will become 4 ways, and 2 2 block can be formed by selecting any two, but this is doing a double counting, right? Because once you select a 2, automatically the second subset is already selected, so you have to divide this by 2. So this will be 3 ways. So you can see by basic counting also that 4 plus 3 is 7 is coming here, right? However, if the numbers are a little big, it will not be easy to do this spacing counting argument. So you should use the recurrence relation here, correct? So we got S of 4 to S 7. Now I will illustrate a nice, I will show you a nice pattern here by which you can easily construct Stirling numbers and partitions. So if n is equal to 0, my Stirling number was 1. This was basically the Stirling number when k is also 0, right? So I'm writing S of 0 comma 0 here on top 1. So I will substitute the value of k here in a bracket like this, right? Now, if n is equal to 1, the Stirling numbers will be 0 and 1, where k is equal to 0 here and k is equal to 1 here, right? Why am I putting it like this? I'm going to make a pattern, just like Pascal's triangle that you might have seen. So I will illustrate that pattern shortly. So basically, this row contains the values of the Stirling numbers S1 comma 0 and S1 comma 1. So what I should do here is I will just draw this, write the Stirling numbers here and put the values here. So let's say S of 0 comma 0 was here, then I will put S of 1 comma 0 here, S of 1 comma 1 here, and S of 2 comma 0, S of 2 comma 1, S of 2 comma 2 here. Why am I stopping at this point? Because obviously Stirling numbers are defined only when n is greater than equal to k, right? So I'm putting the values now. So for n is equal to 2, S of 2 comma 0 is basically going to be 0. s of 2 comma 1 is going to be 1 because two elements in one set, right? And s of 2 comma 2 is also going to be 1, right? Okay, n is equal to 3. Let's see the values. 3 is 0, s of 3 0 is 0, s of 3 comma 1, s of 3 comma 2, and last one will be s of 3 comma 3, right? So 3 comma 1 will be 1, s of 3 comma 2 we just now calculated in the previous question. S of 3 comma 2 had come out as 3, and s of 3 comma 3 will come out as 1. N is equal to 4. I'm putting the values right now. I'll show you how to get a pattern here. 0 1 7 6 1, and n is equal to 5 is 0 1 15 25 25. We had seen 5 comma 3 basically earlier in the previous video. This is 5. So now what pattern am I looking for here? I'm going to write down the recurrence here. S of nk is equal to s of n minus 1 k minus 1 plus k times s of n minus 1 k. This was my recurrence. So let's see what pattern we can discover here. So look at this. This is the n is equal to 3 row, and what we get is this particular value. This particular value is when k is equal to 2 here, right? K is equal to 0, k is equal to 1, k is equal to 2, and k is equal to 3. This is k is equal to 0, k is equal to 1, k is equal to 2, k is equal to 3, k is equal to 4. And here it is, k goes from 0, 1, 2, k is equal to 3, k is equal to 4, and k is equal to 5 here, right? So once we have this, I'll put the values here also. 0, k is equal to 1, k is equal to 2. Now see that if I want to get s of 3 comma 3, right? 3 comma 2, s of 3 comma 2 is n is 3, k is 2. Then it can be written as 1, 1 plus, see this triangle that is formed, 1 plus 2 into this, right? 1 plus 2 into 1 is equal to 3, right? I will just erase this. I'm not going to write the plus and 2. I just want you to recognize that if I had put s of 3 2 here, by this recurrence, what are you getting? S of 2 1 plus 2 times s of 2 2, right? So s of 2 1 is this, right? N is 2, k is 1, and s of 2 2 is this, right? So this value has come by adding this plus 2 times this, right? Let's take any other example also. Let's take this one, right? This one let's take. So k is 2 here, and this n is 5. So you want to find s of 5 comma 2, that should be 4 comma 1 plus 2 times 4 comma 2. So this is 1 plus 2 into 7 will be 15, right? 1 plus 14 is 15. So any place you see you have two numbers in the upper row and a bottom number here, you can always say find the k value for this number. K is 3 here. So 7 plus 3 into 6 is 25, right? 7 plus 3 into 6 is 25. This is called a triangular recurrence. At this place, you have 6 plus 4 into 1 is 10, right? So you might feel like, why is this useful and how can I use this? So you will realize that if I've started constructing my Stirling triangle here, so if you say 1, 0, 1 and write down the first few terms, like at this stage only, now I can start constructing the next set of values. Always the Stirling numbers start with, like this is n is 0, n is 1, n is equal to 2. Always they will start with 0, right? Why will they start with 0 always? Because s of n comma 0 is 0, right? And they will always end with 1. So s of n comma n will be 1. So first and last number of this row will be 0 and 1. That I know. So what about this now? Here k was 0, here k was 1. So if I want to construct this particular element, I should do this plus 1 into 1. So it will be 1. If I want to construct this particular element, I will do this plus 2 into 1, so it will be 3. So I've gotten back the row. 0, 1, 3, 1 was the row for n is equal to 3. If I want to construct n is equal to 4 row, I'll put a 0 first, and to construct this term, their k must be 1. So 0.1 into 1 is 1. 0 plus 1 into 1 will be 1. So I'm constructing basically this triangle here, right? And again, this element will be 1 plus, now k is 2 here for this one. So 1 plus 2 into 3 is 7. And this one will be k is equal to 3. So I have to do this triangle now. So it will be 3 plus 3 into 3, 3 into 1. 3 plus 3 into 1 is 6. And the final element will be 1 when k is equal to 4. So this helps us construct entire rows very quickly. 0 here, and the next one will be 0 plus 1 into 1, so 1. And the next one will be 1 plus 2 into 7, so 15. The next one will be 7 plus 3 into 6, so 25. The next one will be 6 plus 4 into 1, so 10. And the next one will be 1, right? So you can easily construct this set of Stirling numbers by quickly doing that recurrence in your head. So Snk is equal to S of n minus 1 k minus 1 plus k times S of n minus 1 k. So that should help you basically find out all possible partitions of a set of 1 to n into k blocks. So this is called Stirling number of the second kind, and these ways of calculating Stirling numbers are super useful because in real questions you will realize that these arise in many surprising ways. So that's all for this video. We have basically concluded the discussion of set partitions right now. So now we can find out partitions of any set into k identical or indistinguishable blocks. I hope you got something from this video. The next videos will start off different topics where we'll start talking about partitions of integers. So partitions of integers and partitions of sets are actually slightly different. So we'll go ahead to a new topic in the next video. See you next time.